Welcome back to my course Aspects of Biochemical Engineering. Now, in the last lecture I started a new chapter, that is the downstream processing, and I told you the downstream processing plays very important role as per chemical and biochemical industry is concerned, because whenever we market any kind of product, that should be marketed in a purified form, and for the purification of the product we shall have to pass through the different purification processes. So, in this purification process, one most important thing that we have the solid liquid separation process. In the last lecture, we try to discuss about the sedimentation process, we discuss about the centrifugal process. So, and also we discuss about the membrane filtration process. Now, in this lecture, today we will be discussing other different aspects of the downstream processing, which is really in practice in the biochemical industries. Now, first I want to tell you the classification of the filtration equipment. Now, if you look at the classification, that is the filter, this is the filter that we have, and that we have three different types. One is called pressure filter, and there is the vacuum filter, and there is the centrifugal filter. Now, if you look at a pressure filter, we have plate and frame filter press, we have meta filter, and vacuum filter we have the filter lip, rotary vacuum filter, and centrifugal figure we have centrifuge. Now, out of that I want to highlight that plate and frame filter press is largely used in the biochemical industry. Rotary vacuum dry vacuum drum filter, that is also largely used in the biochemical industry, and centrifuge also largely used in the biochemical industry. Now, first let us consider that plate and frame that filter press that we have. Now, a question comes how the plate and frame filter press they look. That let me give you some idea about that. That if you look at this is a plate and frame filter press, plate and frame filter press. Now, how it looks? Now, we know that frame, wooden frame, that in our house we have window, we have door, that door we have, this is the frame that we have, am I right? So, this frame we can have multiple of this frame. This frame we can have different frame, we can bunch together, that one after another, that this frame we can have this. This is the frame that we have, and this frame we can have several frames like this. So, in between the frames, so here this is hollow, am I right? Now, we put some kind of thick cotton pad that in between the frame, and this, since it is made of wooden, we can make a hole in it, and through this hole we can put some kind of nut and bolt arrangement, so that we can fix that. So, in between, suppose this is a frame, and here there is another frame, and there is another frame like this, multiple frame we can bunch all together like this, and when in between this we have one cotton pad we put inside that, and then we pass the liquid in between this cotton pad. So, what is happening, the liquid, suppose this is a cotton pad is wrapped around, and if you pass liquid, the liquid will comes out like this, like this you can collect, and your solid material will be accumulate inside this filter. And when it is totally filled, then you can find out that if you connect it with kind of manometer, that you will find the pressure drop will be very high, and as soon as we have high pressure drop, then you can stop the operation, and take the solid out. This is what is in practice in the baker's industry. So, this is how it looks. This is you can see this is how the different plates, and this is the cloth, this is, you can see that how the cloth is looked. This is the thick cotton pad that we have, that is that in between the plates we have, and we pass the liquid like that. So, what is the basic principles of this plate and frame filter press? Is the surface filtration, and here I want to point out one very important thing, that when we go any kind of filtration process, we design the filtration process on the basis of the size of the particles. Now, we know that in the biochemical industry we use different type of microorganisms, and different type of microorganisms has the different sizes. As for example, bacteria, their size is 0.5 to 2 microns, am I right? And yeast is about 3 to 7 microns, and if you look at fungi, it is couple of millimeter. So, naturally kind of filtration arrangement that we have for different type of filtration process will be different. As for example, for bacterial filtration mostly we go for centrifuge, because particle size is very less. But in case of yeast filtration, because baker's yeast fermentation process, since the particle size is little bit bigger, we go for plate and frame filter press. Now, in case of fungi, since the particle size is about couple of millimeter, we go for rotating vacuum filter, that I shall discuss. So, here this is mostly used for yeast filtration process, that baker's yeast filter, and other purpose also it can be used. The slurry enters the frame, I showed you, by pressure and flow through the filter media, and filtrate is collected on the plates and sent to the outlet. The number of frames and plates are used so that the surface area increases, and consequently large volume of slurry can be processed simultaneously with or without washing. This is the main purpose of this particular plate and frame filter press. This is how it is look. So, liquid, this is thick cotton pad that we have, and liquid entered like this, then liquid comes out here and you drain out like this. So, liquid, you can see the liquid drain out through this. This is the liquid coming out, and liquid this is the in and this is the out. So, liquid and all the solid material will accumulate in between this, and when it is totally filled up, then there will be pressure drop, and from the pressure, when you find out large pressure drop, we stop the operation, open this and take out the solid material. This is how it looks. Now, what are the applications we have? I told you that this is used in the baker's fermentation process. Then the food industry it is used, mining industry it is used, pharmaceutical industry, chemical industry, and wastewater treatment process. So, different we have several applications. We have the plate and frame filter press. Now, let me come to the rotary vacuum filter, where because we know that we have lot of antibiotics fermentation process where we use the fungi. I can give the example of penicillin fermentation process, where we use the Penicillium chrysogenum, which is a fungal strain. I work with citric acid industry, where we use the Aspergillus niger, that is also fungal strain. The size is quite big. So, there we use rotary vacuum filter. Rotary vacuum filter consists of drum rotating in a tub or a liquid to be filtered. The technique is well suited for slurry and liquid with large solid content, and that could clog other form of filters. The drum made up of 3 meter diameter and 3.5 meter length, and give a surface area of 20 meters square. Now, let me explain that this is, suppose this is the drum, and this is immersed in the trough. This is trough. In the trough, we put the fermentation broth like this, and this here we have pipeline. This is, we have pipeline like this, and this drum, this is like this. This drum is like this, and this is wrapped by the thin muslin cloth. Muslin cloth. What is muslin cloth? that is the fine cloth, this wrap on the surface of the drum. Now, what we do here, we applied vacuum at the middle. There is a pipeline. If we applied vacuum, what will it will suck the liquid and the cell mass, and this rotate at very low RPM, maybe 1 RPM. 1 RPM means 1 rotation per minute. Now, when it rotates like this, that the solid material, the cell mass, that will touch on the surface of the thin muslin cloth. Now, here we have a knife, thin knife, that this knife touch the muslin cloth and take the solid material out, and it drop in this particular maybe some kind of screw conveyor is there that will take the material out and put it in some other vessels, or it can put it in the some wagon. So, this is how it is, how this is in practice. Now, principles of this rotary vacuum filter, what do you call RVF? This is rotary, in abbreviation form we call it like this. Now, rotary vacuum filter works on the principle or function of filtering slurry through the sieve leak mechanism on a rotating drum surface under the condition of vacuum. In addition of compression drying using hot air, the removing the filter cake are possible. So, what we let me go to the exact photograph of that particular process. It is like this. So, you can see this is the drum, and this is, here you have fine muslin cloth. You can see here it is fine muslin cloth, this is the fine muslin cloth, and here when it rotates, and this is the trough in which it is immersed, and this trough is rotated at a very low RPM, and here there will be fine knife which touches the surface of the muslin cloth, and the solid material, the cell mass that attached on the surface of the muslin cloth, that will comes like this, it will drop down like this. Okay. This gives a very clear cut picture here. This is the trough where we have the fermentation broth, and it is rotated at the very low RPM. Suppose here it is rotated in this direction. So, it's this is the central duct where suction take place, and it suck the water, and the solid material that the cell mass that adhere on the surface, and this is washing water, just to, if some product is adhered on the surface of the cell mass, that also we take care, that should also come in the liquid. And this is the dewatering zone, this is remain out, so that little bit drying of the material take place, and this is the knife which touches the surface and take the product out. Now, centrifugal filter, there is another type of filter. It is consist of a stainless steel perforated baskets, and let me show you the figure, then I think it will be very clear. This is rotated at the high speed, and then the material will throw on the surface, and here we have perforated disc basket. So, when you throw it, the solid material that adhere on the surface and liquid will goes out. Am I right? So, liquid we can take it out from this outlet, and solid material adhere on the surface of the cloth. This is it consists of, if you look at it, consists of stainless steel perforated basket, typically 1 to 2 meter diameter, lined with filter cloth. The basket coated rotates at a speed typically 25 per second, and higher speed tending to stress of the basket excessively. The product entered centrally and thrown outwards by the centrifugal force and held against the filter cloth. The filter cloth will not allow the solid material to go out. The filter is forced through the cloth and removed via the liquid outlet, and the solid material retained on the cloth. So, I hope that the principle is very simple. The application of this is the preparation of aspirin. This kind of medicine largely used in the pharmaceutical industry for medicinal purpose. This for removing the precipitation of proteins from insulin, and it will also handle the concentrated slurry which might block other filters. So, these are the different purpose where this centrifugal filter may be used. Now, the general technique of for contaminants removal from the liquid relatively to the size of the species to be removed. So, we have on the basis of size we can name the different techniques, like if the size, this is the size of the particle, this is micron, and this range point this 001 to 100 microns. So, if it is very small, we have electrodialysis, then little bit more it reverse osmosis, then ultrafiltration, microfiltration and filtration. Filtration we go for the higher size particles. Microfiltration usually range in between 0 to 10 microns. Now, this is very clear here that this is the membrane filter, and this is the ultrafiltration, this is nanofilter, this is RO. This is how on the basis of size of the particle we can differentiate type of membrane that is used for the separation of particles. So, this is suspended particles that is removed by the membrane filter, and then this is the macromolecule that is can be separated by the ultrafiltration, and then we have like of multivalent ions that can be separated by nanofilter, and RO can be used for the production of the water that we use in the day-to-day life. Now, liquid extraction, another very important area in the downstream processing, that I can give the example of the penicillin industry. That in the penicillin industry, what is happening that penicillin that present in the fermentation broth, and when you reduce the pH of the fermentation broth to 2, then it is more soluble in the solvent layer, that is the amyl acetate or this that kind of solvent which is not soluble in the water. So, when you mix together, then the penicillin will come from the aqueous layer to the solvent layer. Now, when it comes to the solvent layer, then what will happen? In an aqueous layer, you have contains lot of undegraded material or some metabolites. So, since the solvent is and this is immiscible in the water, so you can easily separate aqueous layer from the solvent layer. And then again you increase the pH to 7, then again you water you use, then solubility of the penicillin will be more in water, it goes to the aqueous layer. Again you decrease the pH, then again it goes to the solvent layer. So, like this we can purify the product, and then we can use for different purposes. As far penicillin is concerned, we know the penicillin can be used in 2 different forms, either in the form of capsule or in the form of injection fluid. When you go for in the form of capsule, even a little contamination is there, little impurities is there, we can tolerate because it goes via your stomach. But when it injection fluid, no contamination is permitted, the 100% sterility is to be maintained. Now, let us see that how this liquid field extraction system works. Separate of 2 components of the liquid by contact with a second immiscible liquid as a solvent. So, the extraction is usually used when direct distillation is not economical, and since the solvent usually has to be removed by distillation. The extraction of penicillin from the fermentation broth by contact with amyl or butyl acetate, that is one of the examples. Recovery of acetic acid from the dilute aqueous solution by contact with ethyl acetate or ethyl ether, and separation of high molecular weight fatty acid from vegetable oils by contacting with liquid propane. These are the different applications that we have in the liquid extraction process. Now, liquid extraction method is on the basis of solubility difference of the component of the liquid. I was telling you that on the basis of solubility that this liquid extraction process is used. The extraction operation of the liquid mixture is to be extracted is called the feed, and the solvent is liquid which contact with the feed for solute extraction. Extract is solvent rich product of operation containing extracted solute, and this is called extract phase. So, So, this can be very clear here. So, here see that this is the this is feed and this is solvent. Now in the lab we know that how we do that. We have that separating funnel like this, that we can put two solvent together. This is the this kind of stop clock we have. So, here we can take the two solvent, we can mix together by hand, and then we separate out one layer from other layer. But industry we cannot do it. Industry, what we will do, that we pass the liquid and it is kind of wheel motion that we have like this, so that that two layer will continuously come in contact with each other, and finally then we dispose in the vessel. So, that then one layer will be separated from other layer, we can separate one layer from other. This is how it can be done, shown like this. This is the feed one way, and this is the solvent another way. This is the contacting, the separation, then we do the extract. This is the extract that we have raffinate, that remains, that we call raffinate. That suppose we use the solvent we call the extract, and the raffinate is the aqueous layer. Now, theory of liquid extraction, the raffinate is the spent feed, that while extract is the enriched with extracting solvent. As I told you that penicillin. So, in case of penicillin, it present in the aqueous layer. Am I right? Aqueous layer means water it contains. Another is the solvent. Solvent, what do you have? Amyl acetate, butyl acetate, that we have, solvent that we have. So, now what do you do when you decrease the pH to pH 2, then when we mix together, then penicillin will come from the aqueous layer to solvent layer. So, this is on the basis of the raffinate is the spent feed, while extract is the enriched with this solvent. So, solvent will enrich with the solute. The distribution of the solute between the raffinate and the extract can be expressed in terms of partition coefficient. The partition coefficient, on the basis of partition coefficient, actually we can find out that how quickly the material that can diffuse to the other layer. So, K is equal to C by Cr. C is the equilibrium solute concentration of extracting solvent, and Cr is the equilibrium solute concentration in the raffinate, and the value of K obtained independent on the solute concentration, particularly at low solute concentration. So, this is the how we can do the material balance. Suppose this is the feed. This is the feed that we have, and this is the polymer salt that we have as a solvent, and this is the raffinate. This is the heavier phase, and this is the lighter phase with the extract. And this, if you do the material balance will be F R0. We can F R0 plus RCr plus EC. This is then we can write that extraction coefficient equal to K into E, K into E by R. That is how we can find out this the extraction that factor, the lambda can be defined like this. Now, then this equation we can write in this form, that this is P equal to E C by F R O. This is lambda. We can here you can see the lambda equal to K E by R, and this we use here. Then we can find out these equations. Now, this problem, if we look into that, that conception will be a little bit clear. 100 liters of the aqueous solution of citric acid concentration 1 gram per liter, it contracted with 10 liter of organic solvent. The equilibrium relationship C equal to 100 into Cr square, where Cr and C is the citric acid concentration, the raffinate and the extract respectively, and are expressed in gram per liter. The question is that concentration of citric in the raffinate and the extract, that we shall have to find out, and fraction of citric acid extracted, assume that volume of the feed equal to volume of the raffinate phase. That is the assumption we made. Here what is in the problem, what is given, CR0 is given, that 1 gram per liter is equal to 10 liter, R equal to F equal to 100 liters. Then equation that is given, C equal to 100 CR square. So this is the material balance equation that we have already find. Then we can replace the C by this equation here. Then we can put the value of different values. Then we can find out the value of R, CR we can find out, and C, since C equal to 100 into CR square, we can easily find out the value of. So one is the raffinate, what is the concentration of, what is the concentration of extract citric acid, that we can find it out. The fraction of citric acid extracted in the batch extracted, B can be that equation already given before, that we just put the value here, we can find out the what fraction that can be extracted. So this is how we can solve this problem. Next is the adsorption phenomena. That is another technique that is largely used in the downstream processing. Adsorption is a surface phenomena whereby component of the gas, liquid are concentrated on the surface of the solid particle. Adsorption results from electrostatic van der Waals reactive with other binding forces between the individual atoms, ions and molecules. 4 types of adsorption distinguished from each other. One is ion exchange, physical, chemical and non-specific. Adsorption serve the same function as the extraction, isolating the products from the dilute fermentation liquid. Now let me show you this, that ion exchange adsorption, that that is established in practice for the recovery of amino acid, protein, antibiotics and vitamin. Physical adsorption due to van der Waals force on the activated charcoal is a method long standing for purification of citric acid, particularly for the removal of color. And chemical adsorption of organic chemicals onto the charcoal or porous polymeric adsorption is commonly used for the wastewater treatment process. This is how adsorption can be explained. This we can the adsorbent is the material on which the absorption. So this is the material. Suppose we are talking about charcoal, and this is the adsorbent, suppose methylene blue. So this is how it adhered on the surface of the material. This is the absorbent, and this is what we call, this is the adsorbent, and this is absorbent. This is absorbent, and this is absorbent. Just adhere on the surface of the solid matrix. Now this is the equation that we have, that have adsorbent plus absorbate equal to this is absorption and desorption. If you desorption, then the materials will comes out, and absorption it adhere on the surface of the solid matrix. Now this principle we can express by 2 different isotherm. One is Langmuir isotherm, and the Freundlich's isotherm. That Langmuir isotherm, this is the equation that we have, and kind of correlation that we have is like this, and Freundlich's isotherm, it is little bit the flatted type of thing, and the correlation is like this. So we have 2 different type of correlation for different type of 2 different type of isotherm. Depending on the adsorption characteristics, we can find out which is following in the absorption process. Now next is the evaporation. Now if you look at evaporation, main purpose is the concentration of liquid through a non-volatile solid by boiling away the solvent, that is the water. I can tell you that when citric acid, we because after I told you, after hydrolysis of calcium citrate, we get citric acid and gypsum, and this citric acid concentration is 22%, and this you have to increase to 60%. So naturally you have to remove water from that. And how you do it? We do it very easily. Suppose this is the this is the pipeline, and here we pass the citric acid, and this is the steam we pass, and then we heat it to high temperature. Then we put it in the big like cyclone separator type of things. Tangentially comes like this, and then the vapor will go out. This is vapor will go out, and concentrated liquid will go down. So you will get the concentrated liquid like this. So, this is how it is the removable part of the solvent or the solution from the non-volatile solid because we know citric acid is a non-volatile solvent. This is for concentration of milk, fruit juice, production of sugar, citric acid industry it is largely used. Now, in the performance it depends on the capacity and economy. The capacity is the number of kg of water vaporized or evaporated per hour. Economy, the number of kg of water evaporated per kg of steam feed to the evaporation, and ratio of capacity to economy give the steam consumption of the evaporator per hour. So, this is very important the industrial point of view because what is the money involvement is there. Now, different type of evaporator that we have upward flow, downward flow, and we have upward flow. This is the one is upward flow, then downward flow and forced circulation and agitated flame evaporator. The different type of evaporator is used by the industry. The next is the crystallization process. When we get the concentrated citric acid, then I told you that we reduce the temperature to about 10 to 20 degrees centigrade, then put it in a crystallizer where the crystals of citric acid separated out. So, crystallization is the process of formation of solid crystal precipitating from the solution, melt, rarely deposited directly from the gas, and crystallization is also chemical solid liquid separation technique in which the mass separation of the solute from the liquid solution to a pure solid. So, I can give another simple example of sugar at high concentration at we reduce the temperature, sugar crystals will be separated out from the liquid. If we pass through the centrifuge, we can separate the crystals of sugar from the liquid. And liquid we call it cane molasses, and sugar we can sell it in the market as sugar crystals. We have several applications: production of sugar, purification of drug, improve that bioavailability, preparation of organic and inorganic API, and manufacturing pure API by high yield. This is the different purpose we can use. And theory of crystallization: first is the super saturation of the solution. This is to be done heating, cooling and salting, and then nucleation, then the crystal growth. It can be explained like this, that if you look at this is we concentrated the liquid. This is the dilution of the liquid. Then when concentrated, the particles are very close to each other. Then it coming here. Then nucleus formation take place. When the nucleus formation take place, then the crystal growth take place. This is how the crystal formation that take place. Now, last I want to discuss about the chromatography. Chromatography technique is largely used for the separation of different components present in the reaction mixture, and chromatography is a solute fractionation techniques which relies on the dynamic distribution of the molecules to be separated between the two phases, a stationary phase and the mobile phase. The substrate are separated and differential that distribution between the two phases. The differential coefficient, distribution coefficient will be concentration of component in the stationary phase, concentration of component in the mobile phase. This is how we can express that. Now, application we have several. We have biopharmaceutical production, biopharmaceutical and biomedical analysis, environmental analysis, diagnosis and the process monitoring. The different purpose it is used. We have different type of chromatography. We have gas chromatography, we have liquid chromatography. Gas chromatography is the eluent is the gas, and liquid chromatography eluent is the liquid. The eluent that fluid enters in the column or solvent that carries the analyte. So, suppose this is you inject the sample which and this is the eluent. So, that takes the sample to the column. This is the column where the separation take place, and then we have detector where the detection of the molecules take place. So, this is The stationary phase, the immobilized of the support material inner wall of the column of the tubing. Example is the silica layer, thin layer chromatography, silica gel, alumina and cellulose on a flat. This is the different type of material that is used in the chromatography. So, we have mobile phase that mean the basis on which the particle that we identify, that is the retention time, the after how much time that particular component separated in the by the adsorption column, that we can easily find out that first we inject the standard sample, we find out what is the retention time, then we injected our sample and find out at that particular retention time whether we are getting any peak or not, and on the basis of we can find out this that concept that the qualitative analysis we can find out. But if you want to do the quantitative analysis, then we shall have to inject the definite amount of the sample, and on the basis of that we can correlate what is the amount of that component present in the sample. The visual output, because if you of the chromatograph we can get the peak, as I told you, this is the peak we will get like this, and suppose you inject the sample here, so you know what is the time here. This is the retention, what we call retention time, and this is another retention time that we have. This is another retention time. So, this is for A, B, C. So, if you the more peak you get, that means that this indicates that more sample, that component present in the sample. The different peaks pattern of the corresponds to the different components of the separated mixture. So, this can be represented like this. This is where you inject the sample, and this you will get the peak like this. So, this is like this. This is the mobile phase, and this is the pump, and it passes through this column, and this is the detection from where we detect the sample, and detection mostly either potentiometric or amperometric. So, in this particular lecture, I try to discuss different type of downstream processing, which largely use both chemical and biochemical industry. I try to pick up some example of the downstream processing which is mostly used in the biochemical industry. I have given the example of plate and film filter press, which is used for Baker's industry. I have given the example of rotating rotary vacuum filter, which is used for most of the penicillin industry, where we use the fungi. I have given the example of penicillin, where we use the penicillin chrysogenum. Then we centrifuge we use for the separation of different particulate matters, and then there are other techniques that is also for the separation of the particles. We have adsorption, particularly colored adsorption we do by using activated charcoal. Then finally, I discuss about the chromatography, where we can find out this is mostly used for the analytical purpose, where we can also for the separation of macromolecules we can do that. There were different type of chromatographic technique we have. We have gas chromatography with the high performance liquid chromatography technique. One case we keep the gas as a mobile phase, another case we keep the liquid as a mobile phase. Thank you very much.